Yellowstone Supervolcano formation. A new study challenges the traditional theory. Now we know we've had 3 super eruptions recently, 2.1 million years ago, 1.3 million years ago, 640,000 years ago. We've had a lava eruption 70,000 years ago, and another 80 eruptions since then, according to USGS. Now, according to the University of Illinois at Urbana-Champaign on phys.org, this new study challenges the traditional theory of how Yellowstone supervolcano formed. Recent stories in national media are magnifying fears of a catastrophic eruption of the Yellowstone volcanic area, but scientists remain uncertain about the likelihood of such an event. They're talking, of course, about the event of a super eruption. To better understand the region's subsurface geology, University of Illinois geologists have rewound and played back a portion of its geologic history, and they found that Yellowstone volcanism is far more complex and dynamic than previously thought. They said the heat needed to drive volcanism usually occurs in areas where tectonic plates meet and one slab of crust slides or subducts under another. However, Yellowstone and other volcanic areas of the inland western United States are far away from active plate boundaries along the west coast, said geology professor Li-Jun Liu, who led the new research. He said in these inland cases, a deep-seated heat source known as a mantle plume is suspected of driving crustal melting and surface volcanism. In the new study reported in the journal Nature Geosciences, Liu and graduate student Quan Zhu and Jiashun Hu used a technique called seismic tomography to peer deep into the subsurface of the western United States and piece together the geologic history behind the volcanism. Using supercomputers, the team ran different tectonic scenarios to observe a range of possible geologic histories for the western United States over the past 20 million years. The effort yielded little support for the traditional mantle plume hypothesis. Finally, support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box. They said, our goal is to develop a model that matches up with what we see both below ground and on the surface today. This is what Zhu said. He said, we call it a hybrid geodynamic model because most of the earlier models either start with an initial condition or move forward or start with the current conditions and move backwards. Our model does both, which gives us more control over the relevant mental processes, they said. One of the many variables the team entered into their model was heat. Hot subsurface material, like that in a mantle plume, should rise vertically towards the surface, but that was not what the researchers saw in their models. It did not rise vertically towards the surface. They said it appears that the mantle plume under the western United States is sinking deeper into the earth through time, which seems counterintuitive, Liu said. He said this suggests that something closer to the surface, an oceanic slab originating from the western tectonic boundary, is interfering with the rise of the plume. So could that be part of the Pacific plate? The mantle plume hypothesis has been controversial for many years, and the new findings add to the evidence of a revised tectonic scenario, the researchers said. A robust result from these models is that the heat source behind the extensive inland volcanism actually originated from the shallow oceanic mantle to the west of the Pacific Northwest coast, Liu said. This directly challenges the traditional view that most of the heat came from the plume below Yellowstone. And they said eventually we hope to consider the chemical data from the volcanic rocks in our model. Zhu said, that will help us further constrain the source of the magma because rocks from deep mantle plumes and near-surface tectonic plates could have different chemistries. As for the likelihood of a violent demise of Yellowstone occurring anytime soon, the researchers say it's still too early to know. Of course, they said our model cannot predict specific future supereruptions. However, looking back through 20 million years of history, we do not see anything that makes the present-day Yellowstone region particularly special, at least not enough to make us suspect that it may do something different from the past, when many catastrophic eruptions have occurred, Liu said. And more importantly, this work will give us, they said, a better understanding of some of the mysterious processes deep within the Earth, which will help us better understand the consequences of plate tectonics, including the mechanisms of earthquakes and volcanoes. This is from University of Illinois Urbana-Champaign on phys.org. Please leave your comments and thank you for your support.